Thank you, Raymond. I'm very happy that so many of you are here to listen to me talk about quantum computing and Bitcoin on a Wednesday evening. And this talk will only last for like 1 hour, so it doesn't mean to teach you everything about quantum computing and Bitcoin's quantum resistant solutions, but it will be a starting point. So I hope at the end of the talk, you'll be more interested in these topics than now. And hopefully some of you will go on and learn more yourselves and even work on creating the quantum resistant solutions for Bitcoin. And if that happens, my mission is achieved. And also, at the end, we'll have a quiz. For the winners, we'll have some prizes. From Bit Retail, we'll have some stocks to give away. So, my dad is very skeptical about Bitcoin. Ever since I got into Bitcoin, he's been trying to convince me to sell. He used to say, the government will never give up the right to issue money, so it will never allow Bitcoin to succeed. Imagine how happy I was when we had the first US president endorse Bitcoin. But now, when I talk to my dad about Bitcoin, his major concern is quantum computing will destroy Bitcoin. When this comes up, I always try to brush it off. I would say, when quantum computing happens, like the government's agency will get hacked, the nuclear facility will get hacked, your internet banking will stop working. There will be bigger things to worry about than Bitcoin. How many of you have used that argument before or heard that argument? I see some hands. However, deep in my heart, I know this is a lazy answer. If I really care about Bitcoin, if I really care about my investment, if I really care about the freedom technology, I need to dig deeper into what quantum computing is, what it means for Bitcoin, and what the current development is for quantum computing. So this is what I'll talk about today. So what is quantum computing? Quantum computing basically is a supercomputer that leverages the characteristics of quantum mechanics, which is superposition, entanglement, and interference. So in December 2024, which was last year, Google announced its Willow quantum computer has performed a benchmark calculation, which will take the current most fast computer like 10 septillion years to do, and Willow has done it in 5 minutes. 10 septillion years is like 1 with 25 zeros behind it. It's longer than the age of the universe. And the quantum computer has done it in 5 minutes. So let that sink in. So why quantum computer can be so fast? It's because of its characteristics that it leverages from the quantum mechanics. And the first one is superposition. So what is superposition? Superposition basically is when two. So in the classical worlds, you can the classical computers, it's made of, it calculates using binary bits 0 and 1. You can imagine it's a coin. The coin can either show a head or a tail. But with quantum computer, it uses qubits, which can be a 1, a 0, or a 1 and 0 at the same time. It's hard to grasp, but you can imagine it's a coin that's flipping really fast in the air or flipping really fast on the table. While it's turning, please take a seat. So while it's turning, it's neither a head or a tail, it's a head and tail at the same time. Only when you grab the coin onto your hand or when the coin lies flat on the table, it collapses into one reality, which becomes either head or tail. This is similar to Schrödinger's cat. This is similar to Schrödinger's cat. So when the cat is in a box with some poison, and the poison is released at random time, when you are not checking it, the cat is always alive and dead at the same time. Only when you open the box, the cat becomes live or dead. So your observation will collapse the superposition. So how does this help with quantum computing? Imagine if you have a lock, and the key is a 3-digit binary number. And in total, there's 8 possibilities for this key. With a classical computer, you would have to try this key one by one. And on average, it will take you 4 times to find the key, which is the total number of possibilities divided by 2. In this case, the total number of possibilities is 8 divided by 2. It takes you 4 times to find the key. Whereas with a quantum computer, because it can, with 3 qubits, it can represent these 8 possibilities all at once. But it doesn't mean it will give you the answer immediately. This is a common misconception. People thought, because you can represent all the possibilities all at once, you will immediately know the answer, which is incorrect. Representing the possibilities and finding the right answer are 2 different things. So at this stage, I'll explain later how to find the right answer. But at this stage, you just have to believe me. The number of operations it takes to find the right answer is square root of n. So for a classical computer, as n goes larger, the number of operations you need to find the correct solution goes up linearly. Whereas for quantum computer, it only goes up by square root of n. This is why quantum computer can be exponentially fast than classical computers. Yes?
Why is it not logarithmically faster? Why is it square root?
It's a square root because it's very complicated. I can't really explain.
Are you referring to specific quantum algorithm?
Yes. So for quantum computers, it's always square root. It goes up by square root of n. Yeah, it's beyond like my ability to explain why square root of n, but not logarithmic. But you can look up afterwards why it's. I'm glad you are interested in this. So hopefully you'll go home and watch some YouTube videos or do some research and find out yourself. So this is one characteristics of quantum computing. And another one is entanglement. So what is entanglement? Sorry, I didn't do the slides correctly. So what is entanglement? Entanglement is like when 2 particles are sort of intrinsically linked. So when something happens to one particle, the other particle immediately knows. We can call this spooky action at a distance, because no matter how far these 2 particles are apart, the information can be transferred immediately. And because our qubits, they are small particles as well, so they can be entangled with each other. In a bell, like entanglement, so if the 2 particles are if 2 qubits are entangled, if you measure 1 qubit, the value is a 1, you'll immediately know the other qubit's value is a 1. If 1 qubit is a 0, you'll know immediately the other qubit is 0. But this is just one type of entanglement. There are many different types of entanglements. The value doesn't have to be the same. But as soon as they are entangled, you can view them as one system, and they behave under a certain type of quantum rules. And how is this helping with quantum computer? Because we know that for qubits, they are very, very fragile. There are many different things can make it, can corrupt its superposition and quantum state, so that it can lose its quantum information. Like, for example, heat or electromagnetic waves or like vibrations, it can all corrupt the qubits. But if we can entangle many physical qubits together, we can create logical qubits. And the logical qubits have some error correcting functions inside. So if one qubit is behaving oddly, the other qubits will know, and they will correct that qubit and preserve the quantum information. And for each logical qubit, they only try to hold on to one piece of quantum information. And the logical qubits is a very important concept because that's the building block of a fault-tolerant quantum computer, which is the type of quantum computers we need to hack RSA or Bitcoin's cryptography. And if you have a logical qubits, you can also entangle it with other logical qubits for the computation. For example, if you want to run Shor's algorithm, which is the quantum algorithm that will hack Bitcoin, then you need the input register and the output register. So the input register will contain many logical qubits that's entangled together. And these logical qubits will go through a series of quantum gates, which is designed to just solve that problem. And the answer will be projected on the output register, which is another group of entangled logical qubits. So you can see this it's getting complicated very fast. So but this is how entanglement is helping with the quantum computing to compute. And the final characteristics that helps with the, sorry about this, I didn't have time to check my slides. So the final characteristics of quantum computer is interference. And this is the most, to me, this is the most important one because it helps the quantum computer to find the right solutions. So for interference, you normally think, oh, this only happens in waves. But this is right. In the classical world, things are either made of particles or waves. Like the chairs you are sitting on is made of particles. The sound is made of waves. But in the quantum world, things can be both particle and wave at the same time. And this is called wave-particle duality. And the most famous experiment, I'm sure many of you would have heard about, is a double-slit experiment, where you fire individual electrons through two slits. And if you don't observe them, they will create an interference pattern at the back. So it's like the individual electrons is going through both of the slits at the same time, behaving like waves. But if you observe them, they will only go to one slit, which is the weird part, because it collapses the probability wave. So this is an example of wave-particle duality. Yeah.
Do we know how observation influences the external world? To me, that's a concept that's quite difficult. It's like, well,
yeah.
Does observation mean that in the simple everyday term, like I'm looking at something that tells me that something's happened? Because I mean, most of these waves I can't see. Mm-hmm. So what constitutes observation, and is it understood how that affects the external
observation,
reality?
like either you observe it or even you record it. It can be if you record it but you don't look at the recording, it could be a observation.
Okay.
Yeah, and there are, so you can look this up, but there are very weird experiments has been done, and if you record it and you erase the recording and it changes the results retrospectively, things like that. But it's very interesting. You can look yourself. But for this talk, we just talk about the particles have wave-particle duality. You can behave like both a particle and wave. And our qubits is the same, because our qubits are either photons or ions or artificial atoms. They are very small particles. They have this wave-particle duality. So how is this helping with finding the right answer for the quantum computer? So imagine if you throw a rock in a pond, it creates some ripples. And then the ripples travel, and then it hits a rock standing in the middle of the pond, and it reflects back, and it cancels some wave out and amplifies some waves. This is like what's happening, like if you throw the rock in the pond, but in the quantum computing context, once things are entangled, they are one system. They represent a probability wave. So at one point, the possibility of becoming a 1 is maybe 60% and 40% is a 0. And at one point, it could be a 50-50 chance it's a 1 or 0. It's a giant probability wave. And we could use an artificial rock to help it to cancel out some of the wrong answers and amplify the right answer. And the artificial rock is not a physical rock, but it's a quantum operation called quantum Fourier transform. And this is, so this is hard to understand, but it's the best analogy I can think of is the analogy that you throw a rock in the pond and then the waves canceling out through hitting another rock. So it's a similar concept. So this quantum Fourier transform, it cancels out the wrong answers and amplify the right answers. That's why when you collapse when you observe the answers at the end, it will not show you a random answer. It will have a very high probability of showing you the correct answer. So this is how quantum computers find the answers. So quantum computer is can do very, very fast calculations, but only for a certain type of calculations. It can't do everything. And also, it will never replace the classical computers or GPUs. So CPUs, GPUs, and QPUs will coexist at the same time for several reasons. First, like quantum computer is not good for every problem. It's only good for certain type of problems. And second, quantum computer, for many quantum computers, like to run it, it has to have a very precise like temperatures and so on. You can't just have a quantum computer in your home. It's like many quantum computers has to be like very, very, the temperature has to be very cold, like very, very close to absolute 0, and so on. And also, and also for quantum computers, it's not like a calculator. You can just type in anything for it to do your calculation. Like to solve each problem, you have to design the quantum circuits just for that problem. For example, to do the Shor's algorithm, which is the algorithm that will hack Bitcoin's cryptography, you need billions of quantum gates. So even say quantum computers achieved enough qubits that can say hack Bitcoin, we also need this software, which is the quantum circuits, to be ready to solve that problem as well. And also for the one interesting thought for the coexist of CPU, GPU, and QPU is like, because each will have their merits. So in the future, it might be like AI deciding which part of the problem we send to a CPU, which part is sent to a QPU, and then you collate them, then the AI will collate them together at the end and give you the answer. So what does a quantum computer look like? Many of you may have seen pictures like this with lots of wires. But this is only the outside of a quantum computer. It's for like cooling it and sending the signals, etc. And the actual quantum chip is very, very small. You can put it on your hand. So this is Google's Willow quantum computer's quantum chip. It's very small. And also, it's sort of, so this is Anion. This company is called Anion. It's doing like a superconductor quantum computer. And this is the co-founder showing how the quantum computer is put together. So the chip is inside this cylinder, and this cylinder is made of superconductors to block electromagnetic signals. And also, it's like a Russian door. There are many different shells, one on top of each other. So the second one is for blocking the external magnetic fields. And the third one is for blocking the infrared radiation. And there are some extra ones. And the final one is for creating a vacuum chamber that sucks the inside into high vacuum, so that they can make sure the quantum chip is in the coldest place on the Earth and also the quietest place on the Earth, because the vacuum can help with preserving the temperature and preventing the waves to travel there, etc. But this is, the ones I should show you is for superconductor quantum computers. There are many different modalities of quantum computers, and they all look different. And this is a photonic quantum computer, so it looks different than the other one, from the other one.
Is that the reason why they are keeping them in a glass with the mask? Are they radiating something bad? Or?
I don't think it's radiating anything. It's just like to prevent the dust, I would say, or prevent you, I don't know, like scratch it or something. And there are different modalities of quantum computing. There's like photonic, topological, neutral atom, superconductor, and trapped ion. And there are other modalities, but these are the main modalities of quantum computers. And at the moment, there's no one modality that's a clear winner. So for each modality, there are companies developing on them. The ones that with the most big companies working on them is the superconductor quantum computer. You can say Google, IBM, Amazon are all working for this type of quantum computers. At the moment, the one that's most advanced is a neutral atom modality. And atom computing, which is the leading company that's working in this modality, it has achieved 24 logical qubits last year. And actually, I just saw an announcement today that they have sold a 50 logical qubit quantum computer to the government of Denmark. But I don't think that's delivered. They just sold it, but they haven't yet delivered it. But it means that the 50 logical qubits is not going to be very far away from now.
And how many logical qubits are needed for a short algorithm?
There are
to break 256
So there are different researches, but the common consensus is few thousand. I would say like 3,000, 4,000 logical qubits.
And we are just at 45 or 24.
We are just at 24 at the moment. But this is like growing really fast. Back 2 years, there's no logical qubits. Yeah. So I'll show you the roadmap of different quantum computing companies later. And then like we have the photonic quantum computer, the photonic modalities, which use the light particles. And the advantage of this one is it can operate at room temperature.
Just going back to the short algorithm.
Yeah.
Opposite circuits. So is it for sharp 25, like 256 or?
No, it's
No,
for.
this is different.
It's different.
ECDSA.
I'll go into that later. So hold your thoughts. So where was I? So the photonic modality can operate at room temperature. And it can run very fast, but it's not very accurate. And then for the topological one, that's very mystical because only Microsoft is working on it. And Microsoft claimed they had found a theoretical particle called Majorana. Yeah. And this particle has only existed like theoretically before, and Microsoft claimed they had found it. However, they can't provide any evidence of how they did the experiments, and so no one can replicate their studies. So I would just ignore this track for now and focus on the others. And so many companies and governments has already started to act upon the quantum threat. For example, like Cloudflare, Google, Signal, and Apple, they have all implemented they have all implemented quantum-proof cryptography already. And there are governments that so the governments are also planning on overcome the quantum threat as well. For example, UK is planning to implement all the post-quantum cryptography by 2035, and US is roughly the same. And also, like as I mentioned before, like countries like Denmark, they are not only reactive, they are very proactive. They are buying quantum computers to allow their startups to start working on it, to attract talents that will build on the quantum computers.
I think it's not only Denmark. I think Germany, in Hypro, they are building the quantum center. I think the whole European Union has the quantum strategy. So
yeah,
they are building the quantum centers. Yeah, it's going really fast.
Yes. So I would like. Yeah, many governments, like European Union, even China, are all competing on building on the quantum computers because this will be this will have lots of implications.
It's more than or equal 128 bits.
Sorry.
So that includes 256-bit encryption for this one. So it's allowed after 2035 for ECDSA, which is the Bitcoin's curve.
Yeah, so it will be disallowed after 2035.
That includes 256, I mean.
Yeah.
Okay.
Yeah. So what does this mean for Bitcoin? And also, like all these government companies are working on this. For Bitcoin, we really need to start working on this as well. Because we don't have a CEO, but we are all CEOs of Bitcoin. We are all Satoshis. We need to like step up and work on this because like if no one's like initiating this, it will never be worked on. So what does quantum mean for Bitcoin's cryptography? So Bitcoin has two pillars of cryptography: the public key cryptography, which is for the authorization of transactions and proof of ownership, like proving that you own this address and so on. And the other one is the cryptographic hash, which is the SHA-256, which you just asked before. And that is mainly used for the mining to add another block onto the Bitcoin's blockchain and to validate the network and so on. And for the public key cryptography, the idea is if you have a private key and you can generate a digital signature, and the digital signature can be easily verified by your public key. But if you want to go use just your public key and reverse engineer to your private key, it's very, very hard. This is a one-way function. So an example would be, if I tell you I have a number, 1,295. Now who can tell me which are the two prime numbers that multiply to that number? If anyone can tell me, I have a prize for you. So no one can tell me. However, if I tell you the two numbers are 35 and 37,
You can verify it.
yes, you can easily type this into your calculator and verify that equal to 1,295. So this is a demonstration of the one-way function which secures Bitcoin. And as you can imagine, if the number gets very, very large, it becomes very hard to solve for today's computer. But for quantum, it will be possible. As we talked about before, with about 4,000 logical qubits, you can possibly solve a round-Shor's algorithm that will hack this. Oh, by the way, I forgot to say. So for the public key cryptography, there's two public key cryptographies on Bitcoin. One is the ECDSA, which has always been used on Bitcoin. And then there's Schnorr signature, which was added in 2021 with the taproot. And both of them are based on the elliptic curve, so they are equally vulnerable to Shor's algorithm. And the other one is the SHA-256. This can, with a quantum computer, you can run Grover's algorithm, which can make it much faster to find the hash if you want to create a Bitcoin miner using Grover's algorithm. However, Grover's algorithm is much, much more difficult for a quantum computer to run than Shor's algorithm. So at this point, I would just say we are fine with the mining part of Bitcoin, but we have to give our focus to the public key parts.
Just to say that, in a way, the cryptographic hashing is also used in the proof of ownership, because we don't publish, we don't pay to public keys, we pay to the hashes of public keys.
Yeah, exactly.
And therefore,
Yeah.
if Bitcoin exists on a hash of a public key, that should not be vulnerable to a quantum attack.
Mm-hmm.
But of course, when we publish a transaction,
Yeah.
we've got 10 minutes window, and during these 10 minutes, an attacker could try to recover the private keys.
Yes, I think a lot of the things you said is right. How to say? Yeah, well, I'll explain everything later.
It's
So so you're right. The SHA-256 is also used to generate generate the address from the public key. So before we were using, in Satoshi's era, we were using pay to public key, which you directly pay to the public key. But then later we introduced pay to public key hash, which is a SHA-256 of the public key. But we'll go to that later.
quick question about
Yeah.
the Grover's algorithm. Is that are we less concerned about that because of the difficulty adjustment?
No, it's because it will take a lot more computing power to run Grover's algorithm than Shor's algorithm.
Okay.
You'll need a much, much larger quantum computer to be able to run Shor's algorithm.
Okay.
So if that happens, then we already had a problem with the public key cryptography. So we should focus our attention on the public key cryptography for now.
I think a Grover's algorithm gives you a square of speed up relative to a classical computer. That's true.
Yeah.
And then the Shor's Shor's algorithm, it's exponential increase, right? That's why it's.
Yeah, I'm not too sure. So you may be right, but I'm not 100% sure. But all we need to know is Shor's algorithm is much easier for a quantum computer to run than the Grover's. So there are different ways quantum computer can hack the public key cryptography for Bitcoin. There's long-range attacks and there's short-range attacks. So for long-range attacks, the main target is addresses that has revealed their public key before. And one of this example is address reuse. So it's like you reuse your address again and again. So with, for example, like with Ledger or like with all the hardware wallet, it's supposed to generate a new address each time. But sometimes, from my personal experience, like if I generate a new address, I invoice someone, they haven't paid, and then I want to generate another address, it gives me the same address as I already sent to someone else.
That doesn't reveal the public key. If you
but that's a address reuse. So if both of them use the same thing,
but you need to spend money. You need to spend first. Once you spend, then you reveal the public key. But if you are reusing it and you haven't spent from any of them, then they are safe.
Okay, so if both of them send to my address, they are safe.
Yes, because you haven't spent from them. Because the only point you reveal your public key is when you spend. So if you haven't spent,
okay, makes sense.
But it's
when you spend, you want to spend, and you get your spend everything from that address, and don't use that address again once you spend. So you want your change to go to another address.
Yeah.
But previously, all the wallets put the change back into the same address, and then you're vulnerable.
Yeah. Okay. Thanks for the information. Yeah.
But it's better to create new addresses anyway.
Yeah.
I think it's better practice anyway. But
And so for address reuses, I looked up the top 100 most rich addresses out there. You can look it up yourself using this link at the bottom. And many of them at the top are reuse addresses, and they are all from exchanges. So the top one is from Binance, the second one from Robinhood and Bitfinex, and Binance again, and so on. So if quantum computer exists that can run Shor's algorithm, I would say this Binance address will be the first one to get stolen. And there's a misconception that many people think, oh, Satoshi's wallet is going to get stolen first, which is wrong, because in the Satoshi's era, each address only have 50 Bitcoin in it. So if they have to steal something, they may as well steal the address with the most Bitcoin in it. So this Binance address is the most vulnerable.
Just to say that the reason this is vulnerable, this is taproot address, the 3, and the first and the fourth, is that even if you have not spent from this address, there is a way to recover a public key from this. Whereas with the BC1, you cannot recover the public key. So the BC1 is safer.
Yeah.
Whereas for taproot, you can figure out the public key even if you haven't spent on it.
Yeah. So this, I'm going to go with the vulnerable script later.
Yes.
But yeah, so this one is double vulnerable. So there are other ways you can have revealed your public keys. So there are, if you have used a vulnerable script type, for example, the pay to public key, which is the Satoshi era addresses. It currently has 1.7 million Bitcoin on this type of addresses. And also pay to multi-sig, which is also a very old script type. And then also pay to taproot, as you said, is because it reveals the public key as well.
What is pay to multi-sig? Is that?
Pay is sort of similar to pay to public key, but
But it's not the same as multi-sig.
No. The current multi-sig is new, but this is the old multi-sig. And also, if you have revealed your public key for a UTXO on a fork, for example, on Bitcoin Cash or Bitcoin Gold, and if you owned Bitcoin before the fork, your Bitcoin could be vulnerable as well, even if you revealed your public keys only on the forked chain. And another thing that you could have revealed your public keys is you shared your XPubs to someone, like exchanges or wallets, etc. And recently I had an example that I have to share the XPub to a text software because it wants to track all my movements of my crypto. So I have to share my XPubs. So there are, if you have shared your XPubs, you should remember it. So when before the quantum computer comes, when we have a quantum proof like algorithm, you should remember this and move it. And then there's also short range attacks, which we also mentioned before ahead of me. which is public keys revealed at the time of spend. And this is this can target at all type of scripts. For all of the transactions currently, you have to reveal your public key when you broadcast your transactions. So your money is vulnerable from the time you broadcast your transactions up until like sometime shortly after your transaction has been mined, because there could be reorgs and etc. But for the short-range attack, the quantum computer has to be much more powerful than the long-range attack, because it have to compute your private key from your public key just within like minutes or like hours. And this is an example like of in the inputs of a transactions, you have to enter your signature and your public key. And also there are other attacks. So if elliptic curve cryptography is broken, that means like many other things could have been broken as well. And in these things, it includes like the SSL TLS protocol, which is the technology that creates the HTTPS connections. So that could mean like man-in-the-middle attack. For example, like when you type in the address of the URL of an exchange, the website that's showing to you might be owned by an attacker, and they look like exactly like the exchange website, and you enter your login credentials, and then your login credentials are stolen because your internet is no longer secure because of the elliptic curve cryptography is broken. So there's other type of attacks, and not specifically tied into Bitcoin, but could happen to Bitcoin holders. And so there's people already working on creating the post-quantum sort of solutions for Bitcoin. And one of the and some people, they have always been talking about the Lamport signature, and this BIP 347 opcat in TypeScript, which is aiming to allow Lamport signature. So for those that don't know, the opcat is like, it's a command for concatenating things. And then, so why is this needed for the Lamport signature? So first of all, what is Lamport signature? So Lamport signature is based on SHA-256. So that's different from the ones we're currently using, which is based on the elliptic curve cryptography. So as we mentioned before, to break SHA-256, it needs a much higher computing power. It needs the quantum computer to run Grover's algorithm, which is much harder to do than for it to just break the elliptic curve cryptography. So Lamport signature is considered safer than the current signatures that we're using. And it is a one-time use signature scheme, which means you can only use it once when you do the transaction. When you want to do another transaction, you have to create another private key, public key pairs. And yeah, also I'll show you how it works. But basically, because of its structure, it will make the transaction much longer, and it will take lots of block space. Let me show you how it works. So don't be intimidated by this. I can assure you it's very simple. So just follow me. So if you have a message, like Alice sends 1 Bitcoin to Bob, and you want to hash it using SHA-256, which is the hash we're using for Bitcoin, and you will create a 256-bit number, a number that has 256 digits. And this is the length of your message. So your message you want to sign is 256 digits long. And so in order to sign this, so Lamport signature, they want the structure is it will sign bit by bit. So in order to sign this 256 bit information, you need to create a private key, which you need to create a set of private key, and so you need to create 2 sets of private keys. Each is 256. Each has 256 numbers in it. So in total, you have you have 512 private keys. And why we need this? Because we want to like for if the first digit is a 0, it will have a specific private key just for the first digit 0. If the first digit is 1, you need another private key to represent the first digit is 1. So you need a private key that has you need 2 sets of private keys. Each has 256 numbers. And with this set of private keys for each of these 512 numbers, you hash them and create your public key. And so your public key has 2 sets as well, and each has 256 private keys in it. So you will have 512 public keys as well, which is the public key here. So this is your private key set. This is your public key set. To create this from this, you only need to hash this number to get this. You hash this number to get this. Hopefully you are still following me.
But you only, so this is a binary, right? 0, 1 for the private keys. So
No, the private key doesn't have to be binary. So the message, because you shard 256, so this is binary.
Yes.
This message is binary, but your private key is like this could be a number. It's like any number, just like your normal private keys. It's not a binary number. It's kind of. I mean.
What's the range of here? Is it for numbers on each position? What's the range of numbers that?
For it's just I would say like currently like it's any number.
Like an integer or what is the limit of numbers that can be used here?
Yeah, I'm not too sure about this, so you
Sure,
have to look
that's
it up. But I would think this is the same as the current rules for private keys.
Okay.
But the difference is like you have 512 private keys, you have 512 public keys. And then if you want to sign this message, because it's a 0, so say, like, how to explain this? Like you have a set of so your private key set A is for signing the value if the value is 0. Your private key set B is for signing the value if the value is 1. So this one, the value is 0, so you sign it with the private key set A. And this is 0, you sign it with A as well. And this one, the value is 1, you sign it with your the B set of your private keys. And then once the people, for the people that want to verify your signature, they only need to hash this. So they hash this one and this one, this one, this one, and so on. They hash the 256 private keys, and then they got this part, and they only need to compare it with your public key set to verify is that correct or not.
In this way, we can verify that the person who signed had the knowledge of the private keys.
Yes, exactly.
Because they match the...
Exactly. And so why this is only a one-time use signature? It's because, you already revealed this. For example, if you want to sign another message, but it's like 0, 1, 1 something, like you already revealed, like you already, how to say?
Revealed
Revealed
the
this,
private key.
yeah. So people can like tamper it So people can tamper with your transactions and so on. So you have to discard the private key, public key set for every transaction that you use.
So why this approach is quantum safe?
Sorry?
Why is
Why is quantum safe? Because they use SHA-256. It's not based on elliptic curve cryptography.
No, so why you add the private, so they added private key A and B, which is probably the reason why it's quantum, post-quantum. So I'm trying to, I think this is not SHA related, yeah? I think the trick is the private key A and B here, that it makes quantum safe.
Because the preimage of the SHA-256 function is quantum resistant. Because Shor algorithm cannot figure out or reveal the preimage to any input to a hash function.
Private key would be enough. Why you have two? Because
no, 2 is just for the way the Lamport signatures work.
Yeah.
Because you need one set for 0 and one set for 1. Because you've got a binary message. So that's how the Lamport signatures work. They have two. You have one that would match 0 and one set that matched 1. That's why you need 2. But that doesn't make it more or less safe. The thing that's make it more safe is just that it's using SHA-256, which is quantum resistant. Because you cannot figure out the pre-image to SHA-256 with the Shor's algorithm.
Yeah, exactly. So that's the trick. You cannot reverse it. But so I still don't get it. Why you need to like if it's 0, you use the private key to do the hash, and it's 1, you do the other private key. Because anyway, both of them are reliant on the one-way function, which.
But I cannot know how you did the matching unless you got 2 sets. If you want to sign a message, you sign a message by hashing the 2 sets of private keys. So I know your 2 sets. So when you sign, you sign based on hashing, and so I can then. When I verify, I can make sure that you had the knowledge of the 2 sets. Otherwise, I have no way to figure this out. You cannot do it with 1 set, basically, because you have.
Yeah, for the verification. Yeah.
Yes.
Yeah. Okay.
Okay, so that's Lamport signature used so that will be enabled by this BIP 347. However, there is some concerns about this BIP. First of all, the signature will be very, very large, so it will take lots of space in the block. So